This video is about transforming graphs of tangent, cotangent, secant, and cosecant. We'll also suggest, as always, that you read through the textbook and take careful notes, but then consider the following highlights related to this topic. You'll recall that in the previous topic we discussed the parent functions, or the parent function graphs, for tangent, cotangent, secant, and cosecant. And so let's just briefly review some of those details here. The full development of those is in that previous topic video, but this is just a reminder of some of those things. So for tangent, y equals tangent of x, we have an asymptote at negative pi over 2 and positive pi over 2. That's where the function would be dividing by 0, as you'll recall. Of course, being periodic, that just keeps repeating as you keep incrementing periods to the right or to the left. This is just one period shown. And then, of course, we have a point at 0, 0. When x is 0, the tangent of x is also 0, so we have a point at 0, 0. And then the graph snakes from lower left to upper right. So it's decreasing to the left, chasing the asymptote downward, but then to the right, it'd be chasing the asymptote upward, and we get that kind of snake-like figure from lower left to upper right between the asymptotes as one period. For cotangent, we see some similar things and yet some differences. For cotangent, based on the way that's defined, again as is discussed more thoroughly in the previous video, we have vertical asymptotes at 0 and at pi, and this graph hits a x-intercept at pi over 2, and then snakes downward from upper left, where it chases the asymptote vertically, snakes downward through the x-intercept to the bottom right, where it chases the right side asymptote downward forever. And so again, review those parent function introductions in the previous topic as needed. This is just kind of recalling what we've already discussed on those. And then also I should say, if the whole like x versus t thing, or x and y, if the variables still seem to be a little bit confusing, go back to previous topics where we discussed the choice of variable and how we started using t and then changed over to x. And so there's a couple different uses of the letter x. If that still feels a little tricky, definitely review that previous topic on that, because it helps to get that clear going forward or settled in your mind. Okay, and then we also discussed previously two more graphs, secant of x and cosecant of x. And we have a couple clips of those graphs here. The way that you cut them can vary, and so I've shown here an example where you have vertical asymptotes. In the case of secant, remember secant is 1 over cosine, so you could draw vertical asymptotes at pi over 2 and 3 pi over 2. Remember, those are a distance apart of pi. But then you would keep those going. So like if you kept extending the graph, you'd keep adding pi or subtracting pi, moving left, and find more and more vertical asymptotes. And then between those vertical asymptotes, you'll find these U-shaped branches that chase the asymptotes and then find their minimum value at 1 if it's an upper branch, or their maximum value at -1 if it's a lower branch. So again, review that as needed in the previous topic, just kind of recalling some of those basics here. And then for cosecant, similar and yet different, you have vertical asymptotes at 0, pi, and 2 pi, so multiples of pi occurring in an ongoing way to the right or the left there. And then you have, again, these U-shaped branches that go upward or downward. For the one that goes upward, for example, between 0 and pi, you'll find a branch that goes upward. It has a minimum value at 1, and then it goes upward to chase the asymptotes in each direction. Or moving over to the span between the next set of vertical asymptotes, you have a U-shaped graph going downward with a highest point or maximum top of the U at -1. Okay, and so again, there's a lot of detail that holds all that together that I'm not trying to review completely here. This is now where we're going to say, take those details and let's move further with them. Speaking of which, we're also going to recall some familiar transformation formulas. So recall A, B, C, and D. When we transformed sine and cosine, you may want to recall or review those that video or that lecture. those notes if you'd like, just to make sure that the process is familiar. It's a very similar process for these newer functions, tangent, cotangent, secant, cosecant. In fact, that's why I'm using the same A, B, C, D kind of scheme. It'll kind of help, I think, bring some familiarity and routine to these. You may recall as you look back through those notes of transforming sine and cosine that there was a bit of a process or a set of steps that we follow. Those steps are similar for these functions, but they're different enough for these groups of them that I'm going to give us two sets of instructions, okay? So let's start by talking about the steps for graphing two periods. So that's our goals. It's just a kind of a standard graph two periods. We'll start with secant or cosecant. Secant or cosecant. We'll start with that and find that, yes, these two groups are similar, but they're different enough to, I think, split them out to be helpful. The second set we'll look for, of course, is tangent or cotangent. And there's, yes, a lot of similarities. So let's dig in and see how they might be similar or different. We'll begin in the following with the top option of secant or cosecant. As we've already seen with sine and cosine, if any value is in front of the x variable inside the trig function, factor it out of the entire input as b. We're working with our A, B, C, D kind of setup here as seen in those formulas above. So we're going to find if there's a value in front of the x in the given function, we're going to factor it out just like we did with sine and cosine, and that's going to be our b value. Now, if b, this value that we just discovered in the first step, is negative, we'll use negative identities. And see the previous lesson for those, we talked about that. You'll see it here happening as needed. Thirdly, determine the transformed period and label two periods on the axis. You'll notice that's exactly what we did with sine and cosine, and all it involves is, a quick division with the original period divided by this alternate value of b. So we'll get there and see that in some examples as well. Fourthly, we'll plot vertical asymptotes where the denominator would be 0. And we got a good dose of this as we graphed the parent functions for all of these, tangent, cotangent, secant, cosecant. We did a pretty thorough look at considering when would the denominators be 0. When that occurs, there should be a vertical asymptote in the graph. Same kind of thing here. But now, of course, we're adjusting the period, so that could affect some things. And then let's fifthly, refer to sine and cosine parent functions to plot the min and max values using amplitude, including a vertical reflection if a is negative, a being that leading coefficient. We saw vertical reflections with sine and cosine. Now, this step number 5 is a little bit different from when we transformed sine and cosine themselves, because now we're using those functions, or what we know of them, to help us transform secant or cosecant. Actually, it works out really well. You'll see soon in our examples. The graphs of these are all very related. Sixthly, we're going to shift points and asymptotes So in other words, if we have to shift anything, that'd be like left or right or up or down, then we would do it with the points and the asymptotes. Of course, vertical asymptotes are only noticeably shifted if they shift left and right. A vertical line moving up and down is not really noticeable, but we'll just kind of note all this. Using C for the horizontal shifting and D for the vertical shifting. That's just in keeping line with what we did for sine and cosine. Again, using our A, B, C, and D setup, as seen in our formulas here even previously. And then lastly, a seventh, we'll graph using the parent function shape and direction as a guide, which is why we want to be familiar with those parent functions as well. So our steps will be as follows for graphing two periods of tangent or cotangent. A lot of similarity in these steps as we just saw. There's one slight difference that you'll see. which is already evident if you've been paying attention carefully to these parent functions. But let's see here. Step 1, if any value is in front of the x variable inside the trig function, factor it out of the entire input as b. Step 2, if b is negative, use negative identities. Again, we had those listed in a previous lesson. We'll refer back as needed. Thirdly, determine the transformed period and label 2 periods on the axis, the x-axis that is. Fourthly, plot vertical asymptotes. Where the denominator would be 0. And notice, so far these steps are identical to what we just saw for secant or cosecant above. But there's one slight difference in our next step. So notice now step 5. And this is again for graphing tangent and cotangent with transformations. Step 5 says plot x-intercepts where the numerators would be 0. Okay, so if you were paying close attention when we looked at the parent functions for all of these, tangent, cotangent, secant, cosecant, you'll recall that secant and cosecant do not intersect the x-axis. That's why this step is not listed in their transform steps. Okay, but tangent and cotangent do. So in those cases, we'll plot x-intercepts where the numerators are 0, in addition to those vertical asymptotes that we would have just plotted. And then step 6, shift points and asymptotes, just like previously, using C for horizontal and D for vertical. One thing these graphs do have in common, secant and cosecant, tangent and cotangent, is that they all have vertical asymptotes. And you'll notice that if you, again, just kind of think carefully through all this stuff. And then lastly, refer to tangent or cotangent parent graphs to plot curves as increasing or decreasing. And that's just an important but basic observation of those parent function graphs. If you go back and look at them, you could observe similar kinds of characteristics for secant and cosecant here, but tangent and cotangent, it's good to remember where they're increasing and decreasing and which one is doing which. So those things will matter as we will see. All right, so let's get to graphing. Let's try some examples, huh? We're going to graph the function over 2 periods. That's just kind of a standard way to make sure you're familiar with, how wide the periods are and what they look like, and to be able to see the repetition and all that. And our function given is y equals 1/2 secant of x minus pi over 6. And the minus pi over 6 is tucked in with the x in parentheses, so it's kind of inside the trig function here. So let's notice a couple key things. Number one, we're working with a secant function. That should tell us a lot. We know what that means or how it's defined. But then to get to the details of how to put this on the graph, let's start going through our steps and just kind of note a few things. So A, the leading coefficient way out front, is just a positive 1/2. It's positive, not negative, so there's no reflection, no vertical reflection here. Being 1/2, this means it is going to do a vertical shrink, or in other words, you could say the amplitude is going to be adjusted in some way. We'll get to that in a minute. For now, let's just kind of note A is 1/2. There's not a whole lot to do with that right now. What we also want to note, though, which is more important to getting some progress on the graph, is the B value. Remember, as we noted above, B is what you see in front of the variable. That's just showing inside the trig function. So we have the secant of, and then inside those parentheses, it's just x minus pi over 6. So notice that in front of the x, you don't really see anything, which means the B value is actually just 1. Now, why does that matter? Because, remember, the period of our graph, as we saw with sine and cosine, it's the same thing with secant, cosecant, tangent, cotangent, the transformed period, which helps us kind of mark the x-axis down, is going to be the regular period divided by b. Well, the regular period for secant is 2 pi. And we noted that above. We noted that secant and cosecant, they have the same period as sine and cosine. They're just 2 pi. So we're going to take 2 pi and divide it by b. Of course, b here is 1. So that means the period of this transform function is no different. It's just 2 pi. So with a period of 2 pi, we'll go ahead and mark 2 of those. Remember, we're trying to graph this over 2 periods. So we'll go out 2 of those. Of course, 2 times 2 pi would be 4 pi. So I'm just going to go take a walk further down the x-axis here horizontally and put a mark for 4 pi being 2 periods away from 0, where we have our y-axis, of course, hanging out there. And we want to be able to start putting stuff on here, but there's more to do. So all we're doing right now is just kind of marking enough space to work with. Now, if we follow our steps above, what we've done so far is, okay, so we're doing a secant function. You'll notice in our steps for graphing 2 periods of secant, we've done all the way through step 3 at this point, because we determined the transform period and labeled 2 periods on the x-axis, right? So we know that 2 pi is our transform period, which is actually no different. We marked 2 of them on the axis, which is now listed there as 4 pi. Okay, so let's just kind of keep going where we left off. Next, step 4 says plot vertical asymptotes where the denominator would be 0. Okay, so what are we talking about there? Well, let's recall. Secant is really 1 over cosine. So I'm just going to put a little note about that so we remember what's going on. Or you could say secant of x is really 1 over cosine of x. Probably better to put the x there. And that's a reminder that we are working with division here. Secant is 1 over cosine, which means we might divide by 0 if cosine of x is 0. And that's a problem. Now you may say, well, what about all this, pi over 6 stuff? And okay, don't worry, we'll get to that in a second. For now, we just want to remember where the vertical asymptotes would occur for the parent function of secant. And to get some more items on this axis, let's go ahead and just start cutting things in half like we do, just to get some convenient places on here. So I have 0 and 4 pi marked. I'm going to cut that in half to find a 2 pi. And then I'll cut each of those spans in half. So from 0 to 2 pi, of course, we have in the middle of that is pi. And then from 2 pi to 4 pi, in the middle you would have 3 pi. Just to have some places down to work with here. In fact, we probably want even a little bit more. So let's cut all of those in half again. Again, the nice thing about this is we're just using simple fraction work here. We're just cutting stuff in half. So from 0 to 1 pi would be pi over 2 or 1/2 pi. And then, so now we're counting by 1/2, right? So 0, 1/2 pi, 2/2 pi. Next should be 3/2 pi, or 3 pi over 2. 4/2, which is 2. Next would be 5/2. 6/2, which is 3. And then 7/2. So 7 pi over 2. And then 8/2, which of course is 4. So we have our axes marked up pretty good. Let's see if that's enough to get us going with at least these asymptotes. So we're talking about secant being 1 over cosine, which means we want to know where is cosine equal to 0. Well, you can review that more thoroughly if you kind of comb back through previous sections or look at the unit circle. But remember, cosine is 0 at the top and bottom of the unit circle. So if you're going around one full wrap here, the first place you'd hit would be the top, which is at pi over 2. So in other words, you would have a vertical asymptote at pi over 2 because at pi over 2, cosine is 0, and that would be our denominator, and you can't divide by 0, that's why you get the vertical asymptote there. Now, hold that thought for a second. Let's draw in a few more before we start looking further at our next steps, right? So pi over 2 is where cosine is 0. It would also be 0 at the bottom of the circle, which would be 3 pi over 2. So we'll put another vertical asymptote there. And then if you continue on in the same pattern, notice those are pi units apart from 1/2 pi to 3/2 pi. If you keep adding pi, the way we've marked our axes, that would be like every 2 tick marks. And that's what's convenient about just marking up your axis ahead of time. So if I keep doing that, I'll have another vertical asymptote. So I have one now at pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. And you can kind of start to see the patterns here. You're just kind of counting you're counting by adding 2 to the numerator each time, like 1, 3, 5, 7. Those patterns are really helpful to recognize when you're trying to mark out all these axes. Now I'm going to give a little bit of a recommended pro tip on graphing something like this. So, okay, there's not only one way to go about this or put these steps together. I should be clear about that. But I want to make some recommendations that I think will just kind of help you as you work through this. So instead of actually drawing in those asymptotes right now, we're going to back up and say, hold on, we have more to do, don't we? We have to shift this graph to the right by pi over 6 eventually. So that's a problem because everything's going to be shifting to the right, which means this picture will be a complete mess if I'm not careful. So here's what I'm going to suggest. This is just kind of a pro tip. Instead of drawing all those vertical asymptotes in like that, we're going to get rid of them and just mark where they would be here originally. So notice they're all at the 1, 3, 5, 7 numerator marks for pi. So I'm gonna get rid of all these vertical asymptotes I've drawn, and instead I'm gonna go back and simply circle those places on the graph. So in other words, where we have pi over 2 marked, that was our first one, I'm gonna just put a little circle around that tick mark, and then it was every other from there. So 3 pi over 2, 5 pi over 2, and 7 pi over 2. Okay, now let's remember, that means those are the places of our vertical asymptotes. That's where the cosine values would be 0. Because of that, we'll know that that's where the asymptotes should be drawn or would be drawn. However, we have more to do as mentioned. So let's also just take note that C is pi over 6. Again, that's coming directly from where this function has it. In the parentheses, it was x minus pi over 6. So that means we're going pi over 6 to the right with everything, all the points and all the vertical asymptotes. Well, notice we haven't drawn any points yet, and we did draw the vertical asymptote, but then we kind of backed up. So here's why I think this is a bit of just a helpful strategy. Notice I backed up and I marked where those original vertical asymptotes would be. However, I haven't drawn them yet because there's a bit of a help you can do here, and some people love doing this, some people maybe get past it, and that's fine either way, I guess. I'm going to show it to you because I think it's helpful for some people, and if you get to the point where you don't need to do this, that's also fine. But here's what I'm talking about. If you take the original function, not the original function, the cosine function, because secant is 1 over cosine, then you can actually use what you know about cosine to help you out with. And what I'm talking about is actually where we are in our steps. You go back up here, plot the vertical asymptotes with the denominator would be 0. Okay, we did that, but then we kind of backed off and only circled the places where that would occur. That was like step 4. We'll draw those in later. Okay, step 5, refer to sine and cosine. Okay, so this is now where we are. Refer to sine and cosine parent graphs to plot the min or max values using the amplitude, including any vertical reflection if a is less than 0 or a is negative. Well, in our case, a is positive 1/2. We have no reflection, so we won't have to worry about that. But here's why this matters. If you recall that secant is 1 over cosine, then we can use what we know about cosine to help us get this graph drawn. So recall where cosine would be. I'm actually going to draw it on here, and then don't worry, we'll erase it, otherwise it gets, again, too messy. But I think this is helpful to see. If you go back and review the parent function for cosine, remember where it starts at 0? When x is 0, it starts up at 1 on top. And then, let's see, where does the cosine graph hit 0? Let me just kind of mark this in here. This is cosine of x. So cosine of 0 is 1. Where does cosine hit 0? That's where x is, or where the input is pi over 2. Then at pi, it's negative 1. And then back up at 3 pi over 2, it's 0 again. And then 2 pi, it's positive 1. Okay, so I'm just kind of marking this on here because number 1, it's good review, and number 2, you'll see the direct connection here. If I were to draw in cosine, it would look like cosine and it fits on the exact axes we've already drawn. I'll put it in as just kind of a dashed curve. Okay, and I'll put it in this pink color so we can kind of recognize that's what's going on. In fact, if I were to keep that going according to this pattern, then I could even extend that through 2 full periods, which is what we're trying to do anyway, right? So if I were to keep this cosine going, it would continue to snake through according to all the patterns we know for cosine. And what we would be seeing is cosine, right? That's, in other words, cosine over 2 periods from 0 to 4 pi. Now, why does that matter? Well, notice something. Everywhere that this cosine graph, which I've now put in dashed curve right on our axes, notice where it hits 0. It's everywhere that we've marked as a place where a vertical asymptote would occur. We're starting to see this connection, right? If secant is really 1 over cosine, and you can't divide by 0, then wherever cosine is 0, you would have a problem, or in other words, a vertical asymptote, and that's exactly what we're seeing. So that's coinciding. Everywhere this cosine parent function, this curve we won, which we're not trying to draw ultimately, anywhere that hits 0, we have a place where we would have a vertical asymptote. Interesting. Well, guess what? Wherever that cosine function hits a maximum or minimum, which would be at the top or bottom of all of the hills, that would be a place where the secant function would find its minimum or maximum. Okay, so we're trying to see all these connections. Now let's actually get to graphing them with this last piece of shifting to the right by pi over 6, right? Because we can't forget about that. We have to go to the right pi over 6. So here's the key. I'm going to take everything we have and simply move it over pi over 6. Now you may say, well, that sounds like a mess. It kind of looks messy, but it's better to do it now than any step previously or later, I think. So I'm going to mark in pi over 6, remember that's smaller than pi over 2 for sure. It'd be somewhere just a little bit marked over. I'm going to mark about whatever that span is on your paper. Just kind of mark a little spot somewhere to the right of 0, but only, a little bit of the way. Remember, between 0 and 2 pi, if you look back at the unit circle, you would have 2 marks there. You'd have pi over 6, pi over 3, and then pi over 2, right? So we're talking about just the first one of those for pi over 6. It's just a little bit. So find that little space and take everything you have on this graph and put a mark that space or that amount of space to the right on the x-axis for every single tick mark you have. Just telling you, this is kind of a pro tip here. It's an easy way to get it all on the graph without going crazy with all the fractions, okay? So I've marked now, and I'm going to put the first mark as pi over 6, just so I know, oh yeah, that's right, I'm moving everything to the right, pi over 6. Now it's helpful to use colored pencils or colored pens or something to help kind of keep things organized in your mind if you can. If you can't, it's okay too. But let's see if we can get everything shifted over, because really now, watch this. If I take that original top 0.01, remember that's where cosine would start. We're not graphing cosine here, we're graphing 1 over cosine. So guess what? That is going to become my minimum value. In other words, remember how the graph of secant in its parent function occurred? It had a kind of branch that opens upward or downward. Okay, so if I were to graph this function as is, it would have a minimum wherever cosine had a maximum, or it would have a maximum wherever cosine had a minimum. And you can kind of see this relationship between secant and cosine. Everything's just inverted. Okay, so it's helpful to know that, and that's why I think doing a quick sketch of cosine and this dashed pink curve is actually not a bad idea. Now again, I'm not going to draw all those in completely yet. I just want them there as a reminder. Instead of drawing all those branches in, because it'll get too messy, I'm just going to circle those cosine max and mins so I remember, that's the place where my min or max will occur for my secant graph. Okay, now let's get to actually putting these nuts and bolts on here, okay? Everywhere, remember we had the asymptotes, but we didn't draw them fully because we had to shift everything to the right, but we circled where they would be. So now what we're going to do is go back in and draw them. So I'm going to get my red pen out, and everywhere I had a circled mark on the x-axis, but now I've also put a shifted mark to the right of that by pi over 6. In that shifted to the right place, that's where we're going to draw a vertical asymptote. So if you're following my colors, all my shifted to the right places are light blue, but I'm only going where I used to have or originally had a vertical asymptote. Remember we circled all those places? So to the right of where we had those circled places, I'm drawing in a vertical asymptote on our graph. Circled places, that is, on the x-axis. I circled them all in red to kind of mark down that's where the asymptotes originally were, but we knew we were going to have to move them. So now I'm drawing in all the new ones. Notice they're all just to the right of where the circled places were on the x-axis. Okay, I know it's a lot, but all these little details can really, really help you out. Now, what we're also going to do is draw in our shifted max and min points in the same kind of way. If you think now we've circled them all like high and low. We've circled those min and max points from the parent function cosine dashed graph on there. All we got to do is shift all those points to the right by pi over 6, which I'm going to do with some solid blue or light blue points, all shifted to the right of where those original points were drawn. So we should have a min, a max, and corresponding to all the min and maxes of the cosine graph. But now we have a slight shift to the right, as you can see if you look carefully, from where these now solid light blue points are graphed. They're all shifted to the right according to our shift that occurred on the axis. Okay. So now to draw in the secant branches, wherever I have a shifted max point from what I just did, I just took every maximum point from the parent function cosine, the dashed pink one, I shifted it all to the right. Wherever I would have had a max blue point there is now the bottom of my upward branch. So I'm going to find all those points and draw my upward branch. Of course, kind of keeping in bounds with the asymptotes as well, stuck between the asymptotes. Wherever I had a minimum value or a lower blue point from where I shifted the bottom of the parent cosine function, that's now the top or the max of the lower branch for now my secant graph. Those blue points still being there, hopefully visible enough. Okay. And so what we're actually looking at now is, finally, the branches of this secant function. Now, a quick little note, because you'll be wondering about this, and I want to clear it up right here. So notice that when we did the shifting of pi over 6, we just kind of took all the tick marks we had and just kind of nudged them a little bit to the right to represent that little pi over 6 shift going on, right? And I just said, just kind of figure out how much space it is and move them all the same amount of space to the right. I'm not going to make you go in and label all of those places with specific fractional coordinate marks on the x-axis. You don't have to figure out, what is pi over 2 plus pi over 6, or something else further down the line, 5 pi over 2 plus pi over 6. Like, you don't have to figure out what those all are and label them. All I'm saying is label enough by marking the first span from 0 to pi over 6. That tells us, we're shifting everything to the right, pi over 6, and all the corresponding shifts all the way down the axis can be assumed to be the same amount as long as you're drawing things carefully enough. And that's it. You can now see a shifted secant function. Now there's one thing we haven't quite labeled or accounted for. Can you tell what it is? Go back and look through everything we've done. What have we not quite labeled? Well, it's the amplitude. So remember how A was 1/2? Now it was positive 1/2, which helps. That means it's not negative where we'd have to reflect everything. Thankfully, we'd have to work through that as well, but it's not, it's positive. All that means is we're going to multiply our vertical values all by 1/2. So instead of going up as high as +1, it'll go up as high as +1/2. If we just label our axis, our y-axis that way, it takes care of all of it. So we're going to label a +1/2 for the upper, the bottoms of all the upper branches, and then a -1/2 for the tops of all those lower branches. And if we simply label our y-axis that way, that takes care of the A, amplitude change or vertical shrink, and that covers it. So a lot to it. I assure you that if you pick this apart one step at a time and practice this a few times, it is doable. It's just a lot of detail. And all these steps I have in here are meant to make it easier, but it does just take practice and repetition to get cleaner and quicker with the whole thing. Okay, with that secant graph being done, y equals 1/2 secant of quantity x minus pi/6, let's move on and try maybe a couple more. But there's a lot there, so review as needed. Number 2, our next example begins as y equals cotangent of the quantity 2x minus pi/2. That's all in parentheses after the cotangent. And let's begin picking this one apart with all of its pieces so we know what to do. You'll notice in this case there is something in front of the x. So go back up and look at our steps. That's one of the first things we have to deal with, right? We're dealing with a cotangent function, and in front of the x there's this 2. And remember, you got to factor that out in order to know what the b value is. And so we'll do that right away just to make sure we can see that clearly. Which means I'm just going to rewrite this function. I'll say equals cotangent, and I'm going to use just some brackets to kind of hold this clearly, and then factor a 2 out of that original input, which would leave behind an x minus, and then we have to be careful to know what would go in here so that if I distribute the 2 to it, whatever that is, it has to give me what I currently see there, which is the pi/2. And it may take some practice and thinking through these kind of things, but really, if I had a pi/4 there, think about this. If I distributed the 2 to it, 2 times pi/4 would be, well, pi/2. The 2/4 would reduce, right? So that's how we can tell, there must be an actual pi/4 in there, because now with that 2 factored out, you can see that more clearly. And that's really all we'll need. So that 2 is our b value. Notice here, so then a couple things. A is 1. That doesn't change anything with our amplitude. B is 2. How does that matter? Well, remember, we have to find our period, our adjusted period for this graph, and it's always the normal period divided by b. Well, the normal period for a cotangent, you can check this going up above, is pi. Tangent and cotangent have a normal period of pi. So it's pi/2. That's pi/b, where b is 2. Good to know. That period will help us mark our axis, and that's really where we're going next. Notice in this case we also have a c value. C is pi/4, and since it's minus pi/4, that means we're going to shift to the right when we get to that point on our axis. So now with our adjusted period being pi/2, we want to mark 2 of those out on our x-axis. So I'll just kind of take a walk to the right somewhere, mark a spot, and 2 times pi/2 would be just pi. So I'll mark that down as 2 periods. We'll put down other th/things as needed, but for now, let's start as usual by cutting things in half. So like from 0 to pi, if you cut that in half, you'd have pi/2 somewhere in the middle. Let's cut those in half as well, just to have enough to work with. So we'd have pi/4, pi/2. So if you're counting by quarters, that's 1/4, 2/4, 3/4 would be 3 pi/4, 4/4 would be 1, so there's pi. And then let's see what else we can remember about the cotangent function, because next we want to start getting these asymptotes and things on here, right? So let's recall that cotangent of x, just good to note this unless you've got this clearly in your memory here, but cotangent is really cosine of x over sine of x, right? So we really care about where sine is 0 because we're dividing by sine in our definition of cotangent, right? Cosine over sine. A real good pro tip here is to go back and be familiar with the parent function for cotangent. I'm going to scroll back up to that. We had it above, way back here. We recalled this. In the previous section, we developed these parent functions kind of more primitively, but now we're just kind of recalling some of their details. You'll notice way above here, we graphed the parent y equals cotangent of x function over one period, and notice what happened here, right? We from 0 to pi, we saw one full period, and we had a vertical asymptote at 0 and a vertical asymptote at pi. So in other words, the beginning and the ending of one full period for cotangent was bookends with vertical asymptotes, and then we had this snaky graph in between those. So that's what one full period looks like. We have to get that image, and if we do, it really helps us graph anything transformed. So now, take that image, come down to the graph we're working on. We know that we have a transformed period because now it's pi over 2 instead of pi. But that means that within that span of pi over 2, we should see the same basic image that we saw up in the parent function. That means there should be bookends of asymptotes at those. So from 0 and then pi over 2, we would expect to find vertical asymptotes there. Now I'm not going to draw them because I'm just marking them like we said. We're going to have to shift it all. But for now I'm marking it. That's like we would expect to see one full cotangent graph in that little span there. Now, since I'm drawing two periods, I would also expect to see another one the same distance out. So at the end, at pi, this would be now two sets of vertical asymptotes. So if we were trying to draw them in, we would, and they would look just like our parent function above, but now with two sets for the two full periods. Of course, I'm just marking them. I'm not going to draw them in yet because we're going to have to shift some things. But there we have those vertical asymptote places marked. Speaking of marking, you'll also know if you go back up and look at the parent function for cotangent that it has intercepts. It has x-intercepts. And where do they occur? Well, directly between the asymptotes. So I'm going to mark those as well. Notice I'm not going to plot them yet because we have to shift everything, but I'm going to mark halfway between our two marked asymptote places. I'm going to just kind of by circling these little places on our x-axis, mark where the x-intercepts would be if I were graphing it now without the shifting that we still have to do. So in other words, I've marked pi over 4 and 3 pi over 4 as places that I would be putting x-intercepts. Now, let's kind of get to the place where we can more permanently put some of these things in, right? Because I'd like now to shift everything by pi over 4 to the right. We said earlier that that's part of our function. We're going to have to account for that. And first, just to give us more space to work with, I'm going to extend another tick mark beyond what I had on there because I have to shift everything to the right anyway. So I had gone up to pi. I'm trying to shift everything to the right, pi over 4. So that's like 4 pi over 4. One more would be 5 pi over 4. It's good to label this correctly according to our current scale. Just to have a spot over there, a tick mark over there that we can use as we shift. Now, we're going to shift everything to the right. So what I want to do is kind of mark that. Let me pick on a light blue color. So I'm going to shift everything that far to the right, which happens to be one tick mark the way we've labeled them. So that's actually kind of convenient. All we're going to do is shift everything to the right one tick mark, which means if I coordinate this in appropriate colors, I was going to have a vertical asymptote at 0 and pi over 2 and pi. We marked those already by just kind of circling them. Instead, everything's going to be shifted to the right, which means my actual vertical asymptote is at pi over 4. I'll now draw one in there. And so that kind of moved over. Instead of pi over 2, we move over. I have one actually at 3 pi over 4. And then instead of the marked pi, same thing, shift over. Now we have one at 5 pi over 4. And one quick note about these trig graphs. I'm just kind of picking on a certain, portion of the graph to put. You could also, if you wanted to kind of use some of the space to the left, you could do the same thing. Remember, they're periodic, they just keep repeating. So I'm shifting everything to the right, which will look the same no matter where you start shifting it, right? But you can have some variation in how much of the graph you clip or draw on your paper. Okay, so now we've drawn the final asymptotes. We haven't drawn the final x-intercept, so let's do those next. We're going to mark those in kind of a solid blue color. Remember that we marked where they would be. Like, there was one that would have been at pi over 4. We circled it there, but I'm shifting everything to the right, so now it's actually at pi over 2. I'm going to mark it with a solid point there. Again, I had one marked. It was at 3 pi over 4. Move to the right. Now it's actually at pi. I'll put a solid point there. If we mark those that way, then we'll have a better idea of how to draw our final graph. And you'll recall again, there's no vertical reflection in this function. A was positive, so we don't have to worry about flipping anything upside down. We're just going to kind of keep it as is. If you go back and refer to the parent function for cotangent, way up at the top, remember it starts high on the left and then snakes down low to the right. So all we have to do is make sure we basically see the exact same thing within every period we're graphing. We're graphing 2 periods, which means between the asymptotes we should see that. So using our intercepts and asymptotes, we can just kind of snake through to draw exactly that. High to the left, low to the right, but that happens within each period. And we're graphing 2 periods, so it happens twice. Now, like I said, you could graph any set of periods you want. So if you had started a little bit further to the left, you might recognize that you would have an intercept right at 0, 0, and your graph would all snake through that. It just keeps repeating to the left, or if you went further to the right, it would repeat there as well. That's the whole point of these periodic functions. They just keep repeating. But for now, we've kind of focused in on this portion, and I've graphed now this originally given function, y equals cotangent of the quantity 2x minus pi over 2, all in parentheses. That's now what you can see in 2 periods, kind of just right in the center of our graph, with all of those transformations occurring. But really, you could have just as well, if you're graphing 2 periods, you could graph maybe the 2 that are all the way to the right, or the 2 that are mostly to the left. There's a lot of options there. I've just kind of graphed something centrally located. But the point is to graph 2 periods and label everything correctly. Alright, let's move on to a next example. This next one is given as follows. Y equals -2 cosecant of the quantity pi x minus pi over 3, and that's all in parentheses. Alright, so we'll start from the top. As always, we're trying to understand how our transformation formula kind of fits onto this so we know what's going on. You'll notice in this case we have an a value of -2. We'll get to that in a second, but notice we're going to have to factor out something from what's in the parentheses. How do we know that? Because there's something in front of the x, and as soon as we see something there, we know, okay, so let's rewrite this. So I'm going to rewrite this whole function as -2 cosecant of, I'm going to use the brackets kind of like I did previously because I want to factor out that pi from both of the terms inside those original parentheses. That means I would be left with an x minus, now again, think through carefully what would have to be here so that when I distribute the pi in here to these new parentheses, I get the original quantity. That's the whole point of us factoring this out here. Okay, so if you think that through, it should be, I think, 1/3, right? If you distribute a pi to 1/3, you'd have, well, pi over 3. So that means that gives us our c value, the shifting we're going to see in our graph. I'll close up the brackets. We're done factoring. There's no d value on the end, so there's nothing else to do there. So now let's just kind of take note of what's going on. We have a out front, the leading coefficient of -2. That means we do have a vertical reflection, right? If a is negative, you got to flip the graph vertically. So just take note, that's going to have to happen because it's negative. Now because it's 2, it's also going to have a vertical stretch, okay? But again, that kind of gets taken care of by just the way we labeled the vertical axis, so I think we'll be okay there. We have a b value. Remember, b is the thing that we factor out. In this case, it was pi, which means the period of our graph, our new transformed graph, is the basic or original period of cosecant divided by b. Well, the original period of cosecant, as you can recall from above, would be 2 pi. So it's going to be 2 pi divided by pi, which is, well, just 2. Okay, so our period's just 2. It may be a little strange to have a whole number, but that's fine, it'll work. And then, of course, with our c value being 1/3, which was not evident until we had factored out the pi, and then you can kind of see it here, x minus 1/3. It's our c value. That'll be shifting things to the right. Okay, we'll get there eventually. There's no d, or you could say d is 0 here. There's no shifting upward or downward. Okay, so there's a lot going on. Let's keep with our steps of not only identifying all these things, but then marking out our axis. Let's draw out or mark out 2 periods on our axis. So if our period is now 2, the adjusted one, we'll go twice that out, which is 4. Of course, we're starting with 0 and at our origin. And then we'll start cutting things in half like always, because it's just a convenient way to get things situated with very usable tick marks. So halfway between 0 and 4, in the middle there would be 2. And then we'll cut all those in half. So between 0 and 2 would be 1. Between 2 and 4 would be 3. And now we have some useful places marked on our x-axis that we can start using for setting up the important things, asymptotes, intercepts, and so on. Now let's also keep a very close eye on the parent function here so we don't forget what's going on and what we're even working with. So cosecant, we recalled these earlier on in this set of notes. We developed it more thoroughly in the previous section or previous topic. So cosecant has a couple branches to it, and those branches, of course, are surrounded by vertical asymptotes. And this is, remember, when we recalled the parent functions above, we just did one period of them, and for tangent and cotangent, you see a single curve between 2 asymptotes for one period. For secant and cosecant, you see 2 branches and 3 asymptotes for the parent function. So notice here, for the parent function of cosecant, you see an asymptote on the left, right, and middle for one full period. So let's now go down to our transformed graph and see if we can kind of put this in place. We're looking at 2 full periods, which means you would expect to see 3 asymptotes in each of those periods. Left, middle, and right. Or in other words, if we mark where our vertical asymptotes should be, remember we're just going to mark them by circling the places in red on our axis here. Before we do that, let me recall or write down here. So let's not forget, cosecant x is really 1 over sine of x. That just helps us remember what we're working with here. And we don't want sine of x to be 0, otherwise we're dividing by 0. That's where vertical asymptote would be. So now the question could be, well, where is sine 0? But again, we have a completely differently labeled axis here, so that might not be useful to go back to the unit circle on that. That's why just looking at the parent function above can be so helpful. And like we saw previously, even recognizing or remembering the parent function for sine can be super helpful here. So let's recall the sine function, sine of x, just the parent function. Remember, it starts at the origin. But, actually, we should be really careful here. Remember this negative sign that was in front of our function? And we noted this over here when we said a is -2. This was going to be vertical reflection. Well, here, we better kind of mark it here. So instead of just looking at the parent function for sine to get some of these characteristics in here, let's suppose it's negative sine. Because we want to remember exactly where things are going up or down. So negative sine, again, to go back, you can review where sine is, and then if you flip it upside down, it would start at 0, 0. It would, since it's negative, it would go down and then up and then back down to the axis. So this is negative sine because of the negative that we have in front of our function. And catching it and doing it here, this vertical reflection, is probably the easiest way. It's It's easy to forget this and then get to the end and go, oh, that's right, I have to flip everything upside down, and then it's just way more difficult. So if you can catch it here, it's helpful. This tells us that within one period of our function, we have within one period of sine, we know that the negative sine function looks like this, 3 intercepts. For this particular function, one period is 2, which means if I circle where those x-intercepts would be for the sine function, it'd be 0, 1, and 2, like to catch all these points here with one period of sine. Why does that matter? Because again, cosecant is 1 over sine, so when sine is 0, we'd have our vertical asymptotes. So I'm marking the places where those vertical asymptotes would be, 0, 1, and 2. Of course, this just continues, so they'd also be at 3 and 4 every unit. Now, that's where the vertical asymptotes would occur if we were doing nothing else. Of course, we are doing some other things. We have to shift everything to the right. So let's now consider what that's going to do. We know that c is pi over 3, and then it's going to be to the right because it's minus pi over 3, and we use the opposite of that sign. So that means everything I have is going to be shifted 1/3. Now, like we did previously, we're just going to mark this and kind of eyeball it. So it's easiest to go from 0. I'm going to go from 0 to about 1/3 of the way between that and 1 and just mark that as 1/3. Of course, every place is going to move that much. So just kind of eyeball now what it is. And if you mark them all the same distance visually, you don't have to go through and label every fraction. It'd basically just be adding 1/3 to all of our x marks. So it'd be, 1 plus 1/3 would be 4/3. If you wanted to go through and mark them just to be super clear, that's fine. 2 plus 1/3 and so on. You just keep adding 1/3 to all our marks, but as long as you have at least the first one labeled, you can just kind of mark the same distance away from the labels you do have on the axes and use those as just kind of the anchors for this. So we have that shifting marked, and we were going to put all of our vertical asymptotes where sine is 0 at these red circled places. Now we're going to be moving those all over, so really they're occurring at all these multiples of 1/3. So now let's actually draw them in. Our vertical asymptotes are going to be first at 1/3, next at 4/3, next at, again, all these places that we've now shifted to the right. You don't have to label them all with fractions, as long as they're clearly marked, the same visual distance to the right of all your x markings. Okay, so that's where our vertical asymptotes will be. Now, you'll recall, if you go back up and look at the sine parent function, it's good to do this, or not the sine parent function, the cosecant parent function, way up at the top. There it was. So we recalled this earlier, that the cosecant parent function has 2 branches within one period, and those are reflected in where the, in this case, sine function would be defined. Remember, cosecant is 1 over sine, so you might imagine a sine function kind of drawn in with it, and you can spot where the mins and maxes would be. We did that more in the previous lesson video. You can go back and rewatch some of that. But the same thing applies here. So within one period, you would expect to have this kind of pattern where the maxes and mins are shown. So in that case, we'll take a look at each of these and sketch in this parent function for negative sine just to get an idea of what this will look like. So remember, we're starting at the origin, and then we would expect intercepts at all these places we've already circled. It's kind of overlaying this. And we would expect negative sine to go down, and then up, and then down again within those spans. So we're seeing this kind of pattern visually. Now the reason that can help is because, remember, if cosecant is 1 over sine, then at all of these peaks and valleys of the sine function, you would have the, well, peaks and valleys of the cosecant function. So let's mark these in. At the first low point, at the bottom of where that negative sign would first hit, yet now shifted to the right by pi over 3, so the same amount we've shifted everything already, pi over 3 to the right, you would expect to find a point, and guess what? That point is where you draw the first branch for our graph, going downward since it's in the lower half. Moving over to the next spot, again, you'd find the next peak or valley. It's a peak, but that would be shifted over by that same amount, 1/3, and you'd have a point there. And if drawn to scale, which by hand is always a little tricky, these points after shifted should be directly, in between or in the middle of asymptotes. So, they're not always perfect if drawn by hand, but that just for a reference, that's where they should be. And you can kind of spot it. It doesn't look too bad if you're careful in graphing things by hand. And you're getting these sets of branches in opposing directions, just like the parent function. And again, 2 sets of branches would be 2 periods for this based on the way it's defined. Okay, let's move on to another example. Okay, in this 4th and final example for this video, I know it's a lot of detail here, we're given the following: y equals the tangent of, and then in parentheses following it is -2/3 x plus pi over 6. That's all in parentheses. So let's start picking this apart and following our steps to identify the transformations and so on. Notice that there's nothing in front of the tangent, so the a value is 1. That's fine. There's no amplitude change or vertical reflection. But now notice, looking inside the parentheses, there's definitely something in front of the x. And as we know, we have to factor that out immediately. So let's start with that. We're going to rewrite this function as tangent of, and then I'll use the brackets in keeping with what I've been doing. Take that coefficient of -2/3 that was given in front of the x. Factor that out, though, of the 2 terms that are in there, which would leave us with, can you pause it and check it? It'd be an x, and then you have to figure out what after the x, when the -2/3 is distributed to it, would give you what we're seeing in there, which is pi over 6. So in cases where that gets a little challenging or not easily spottable, here's a little pro tip, okay? So to figure out what needs to go in these parentheses, or inside the parentheses, so that if I were to distribute the -2/3 to it, I would get what I'm looking at in the actual result, which is the pi over 6, right? If it's not obvious, here's a little thing you can set up and just use some algebra for it. You can say, what you know is that, I'll do this down here, you have -2/3 that you're trying to distribute in times what? I'm going to give that what a name. I'm just going to call it the letter A. So -2/3 times A, whatever that is, has to give me what I'm expecting there, which is the pi over 6, right? So you're kind of setting up your own algebra problem, but then it's a super easy one to solve. How would you solve for A in this? Well, just multiply both sides by the reciprocal of this fraction, which is -3/2. So A equals pi over 6 times -3/2. And then you can simplify this. It'd be a pi on top. It'd be a negative. And then, let's see, 3 over 12 would be 1 over 4, so -pi over 4. That's just multiplying these 2 fractions together, okay? What the point is that's really A. What was A? A is whatever you have to multiply the 2/3 by to get the pi over 6, which is exactly what we're trying to figure out. So it turns out it'd be a negative pi over 4. That has to be inside those parentheses. So that when I distribute the -2/3 to it, it gives me the pi over 6. How do we know it'll work? Because we just figured it out, right? -2/3 times A is pi over 6, and A, of course, is -pi over 4. So A is what should be in there, which means -pi over 4. Now let's start to piece this together by identifying each part, right? We know that A is 1, nothing fancy happening there. In fact, nothing happening there. B, that now that we've done the factoring, B is the number we factor out, right? So we figured out that's this -2/3, or that was kind of obvious at the start. That's B, which means the period of our graph is going to be, remember, it's the original period divided by B. Well, the original period of tangent is pi, so it's pi divided by or you can just use the, okay, back up. Okay, glad I caught this. So this is easy to miss. Notice how B is negative, or how there's a negative there. So we forgot. I'm going to use the negative identity. This is actually the same thing as, remember, tangent is an odd function. So this negative can just be thrown out in front because tangent is odd. Again, go back and review negative identities if you'd like in a previous lesson. But this is the same thing as, this will help us out, negative tangent of 2/3 times x minus pi over 4. So that's all that changed. We can just kind of rewrite it that way with the negative there. It just kind of simplifies what's going on. It does mean, however, that there is a negative in front, and that tells us that A is actually a -1, which means there's a vertical reflection. Okay, so that's A. B is the number we factored out. That's 2/3. And we find our period by doing the original period divided by B. Well, the original period of tangent is pi. So we're looking at pi divided by 2/3, which means we have 3 pi over 2 as our period. Okay. We also are going to shift. We'll just kind of note for now that C is going to be pi over 4, so that'll be shifting to the right a little bit. All right, now our next step is to start getting something down on this graph in terms of axis, marks and things. So there's a little bit of I don't want to call it a trick, but something really to consider with tangent. And normally we get our period, our new adjusted period, which we know is 3 pi over 2. We've already kind of figured that out, right? And we graph 2 periods on the graph, since that's our goal, to graph 2 periods. However, let's remember something very important. If you go way back up to the parent function for tangent, which we brought in as some review in this topic, we kind of established it a little bit more introductorily in the previous topic. You'll notice, okay, so let's look again at the parent function for tangent. What do you observe about this? Maybe in comparison with the parent function for cotangent that's next to it. So there's some differences. Do you observe that, among many things you could describe, do you see how the set of asymptotes, at least that I chose to display, kind of straddle the y-axis? In other words, there's not a vertical asymptote right on the y-axis, right? There's one to the left of it, one to the right of it. There's actually an intercept right on the y-axis. And that's different from cotangent, which has a vertical asymptote right on the y-axis. Okay, so what does that mean? Well, practically speaking, for drawing a good-looking graph, here's one extra little trick I'm going to jump. This is just a little bit of a pro tip. Notice that what you see with the asymptotes straddling or spanning or surrounding the y-axis is that if you really were to take like the distance from one asymptote to the other, that's really from negative pi over 2 to positive pi over 2. How far is that? Well, it's pi, right? Yeah, that happens to be, well, the period of tangent. So as we've already discussed, one period of tangent would be the space between one pair of vertical asymptotes. So if that's the case, then let's kind of leverage that parent function pattern and know that really we want the period spanning between a set of asymptotes, and you could start them this way. There won't be one right on the y-axis for the basic function. Okay, let's go back to our graph and see what we can do to make sense of this in terms of drawing where we are. So we have a period of 3 pi over 2, right? That's what we already discussed as our adjusted period. So if you cut that in half, that's how far you could go on either side of the y-axis to mark out your asymptotes. Let me say that again. If you take your period length and cut it in half, that's how far you can go to the left and right of 0, your y-axis, to mark your asymptotes. We're not taking into account any of the shifting yet, but let's go see if that actually makes sense. If you go back up to where we just were, looking at that parent function for tangent, right, that period is pi. If you cut that in half, guess what you get? Pi over 2. And that's how far you go to the left and to the right to mark your first set of vertical asymptotes. So that's just a helpful little pro tip visually and practically to help us graph something here. If our period is 3 pi over 2, then cut that in half. What do you get? Well, you get 3 pi over 4. So I'm going to mark this down. 3 pi over 4. I'm going to go that far to the left and the right of 0, which yes means negative 3 pi over 4 on the left, positive on the right. Okay? That means that we would expect to find asymptotes maybe there. Of course, we haven't shifted anything yet, but that's a good anchor for how we're going to start setting up some of the structure of this graph. And since we're trying to graph two periods, if this distance is 1 period, which, how far is that again? Oh yeah, it's 3 pi over 2, right? That's what we kind of started figuring out, right? That's 3 pi over 2, but we've split it in half and sent 1/2 of it to the left, 1/2 of it to the right, surrounding 0. Why? Because that's what the parent function for tangent does. Well, we want to graph two periods. Let's just extend another one in our space, right? So this distance is 1 period. Let's extend that same distance to the right further and extend another one here. Now, how far would that be? Well, let's do the math, right? We know we're at 3 pi over 4 at this marking. We're adding 1 full period, which is 3 pi over 2, also known as 6 pi over 4, if you just kind of keep a common denominator there. So 3 pi over 4 plus 6 pi over 4 would be 9 pi over 4. In other words, now what we're showing are 2 consecutive periods of this function. Okay, now, we know what the graph should look like in those, and we know that it would have vertical asymptotes on all these marks we have so far. So I'm going to just circle those in red, kind of like we've been doing. We're not going to draw them yet because we do still have to shift. So next, let's recall that we're going to shift, and we'll do so, what did we say? Oh yeah, pi over 4, we're going to go to the right because we have this minus pi over 4 in after our x for our function. So I'm going to kind of just mark again a little bit. You know, how far is pi over 4? Well, hard to say. I'm just going to mark a little bit over from where those marks are. If you want to, remember, it's good to label maybe one of these marks, these new marks. It's pi over 4 to the right. Well, what is 3 pi over 4 plus pi over 4? Well, it's pi. So our first mark there to the right of 3 pi over 4 would be pi, which means we're going to have a vertical asymptote there. If you mark at least one of these new places, you don't have to mark them all. Of course, you can if you'd like. You're just adding pi over 4, and our markings are already in that common denominator. So like, let's see, 9 pi over 4 plus pi over 4 for shifting right would be 10 pi over 4, also known as 5 pi over 2. So you can label that one. Let's see, negative 3 pi over 4 over here on the left side, plus pi over 4 would be negative pi over 2. You can mark that one if you'd like. And the point is, that's now the place, the final resting place for our vertical asymptotes. So we're going to go ahead and draw those in now. And again, our goal is to graph 2 full periods of this. You could extend those further to the right or the left if you wanted to graph more. What we now know is, based on the parent function of tangent, again, way up at the top, we know that we have our asymptote spread, and we know we'll have an x-intercept right in the middle of those. So with that, let's see if we can finish off what we have for this function. Again, there's been a lot of changes to it, but so far we know that those are the vertical asymptotes. That's good to know. And we now know that there's going to be an x-intercept halfway in between them. How do we figure out where that is? Well, let's just do a little bit of arithmetic. So we're trying to find the middle between negative pi over 2 and pi, right? Because that's where the asymptotes are. Halfway between them would be an x-intercept. So we just average those two numbers. What is pi plus negative pi over 2 divided by 2? Now that sounds a little crazy, but it's just arithmetic. I'm adding these up and dividing by 2. That's finding an average, right? That'll be the middle ground of it. So pi plus negative pi over 2 is the same thing as pi minus pi over 2, which is pi over 2. So really I have pi over 2 over 2, which is really pi over 4. So what does that mean? That means at positive pi over 4, I will have my x-intercept. Now you can do the same thing for the next set, but before we do, let's draw one of our branches here. Now remember, there is a vertical reflection, so you might recall above that the parent function for tangent goes low left to high right, increasing from left to right, but we're flipping that thing upside down, which means it's going to go in the opposite direction. So this time we're going to go high left to low right, but still snaking through in that kind of pattern, because again we have this vertical reflection going on. Okay, so that's one of our branches. We're trying to graph two periods, so we'll find the next one as well, which would be the average between pi and 5 pi over 2. Let's do the same thing there, add those up, divide by 2. So let's see, that would be pi plus 5 pi over 2, all over 2. Okay, common denominator of this would be 2 over 2 pi plus 5 over 2 pi would be 7 over 2 pi. So that's 7 pi over 2, also known as 7 pi over 4. And that must be where our next x-intercept is. It's halfway between those two. And we know we're going to have the exact copy of the snaky looking curve through those. And there we have it, two periods graphed. Of course, you can extend those further to the left or the right as you see fit, but there's a lot of detail in there in terms of getting the axis labeled correctly. So carefully comb through that, watch again, and enjoy.